Okay. So the contour map over intervals of 4. Now we have a contour map up here. So as the C's increase, should be going along. Yeah. So notice with this contour map, as the C's increase, then we're moving down the y-axis, and then as C's go negative, we're moving up the y-axis. So that matches our graph. Okay. Let's look at the official explanation. So sketch the graph. So note that if we said z equal to f of x, it becomes a plane. So this is the equation of a plane. So to plot, we just find the intercepts, we plot the intercepts, and that'll give us our plane, as we see here with the 6, 4, and 12. That was fine. So in general, the level curves of a linear function are the lines with this equation. Therefore, the contour map of a linear function consists of equally spaced parallel lines. So in our case, the curves and the lines, the level curves are the lines 12 minus 2x minus 3y equal to c, or 2x plus 3y equals 12 minus c, figure 14. And that's what we got for our contour. So as we plotted our different contour lines, we got parallel lines that are equally spaced. Okay, so let's continue. So that was example 7. Let's go like this, paper, get rid of that. Okay. Okay. So then the next notion, let's see. So how can we measure steepness quantitatively? So let's imagine a surface given by z equals f of x, y as a mountain range. So in fact, contour maps, also called topographical maps, are used extensively to describe terrain, as in figure 15. Okay. So we place the xy plane at sea level. So when z is 0, make that sea level. So that f of AB is the height. So the outputs are going to give us the different heights, also called the altitude or elevation of the mountain above sea level at the point A, B in the plane. Okay, so we want to get a sense of, we want to calculate the height or the steepness quantitatively. Okay, let's see. So in calculus, when we're talking about steepness of a between 2 points, so you have one point and a second point, we're talking about how steep is it. We're talking about slope or average rate of change. So, so we introduce this notion of average rate of change from P to Q. It's basically going to be the change. It's like, so in the 2D sense, it's the rise over the run. In the 3D sense, it's the change in altitude over the change in horizontal. So that matches the whole rise over run notion that we know from the past. Where the change in our altitude is going to be the change in the height from P tilde to Q tilde. And then the change in the horizontal is going to be the distance from P to Q. Now what is P tilde? So if we look above, it says figure 16A shows 2 points P and Q. So where's 16A? Oh, it's not here. Okay, we have to. We need to pull up the next part so we can get rid of this. So figure 18. Did I miss a page? Did I just delete it? Here it is. So 16A. So we have 2 points. The altitude, P tilde and Q tilde. Okay. So it looks like we have 2 points P and Q on the contour map, and then the alternate points in the 3 space is P tilde and Q tilde. So the change in altitude is how our z's are changing. So we're going from what z level to other z level. All right. So let's go back. So in figure 16a shows 2 points P and Q in the XY plane, together with the points P tilde and Q tilde on the graph that lie above them. We define the average rate of change as the rate of change from P to Q, or in other words, the steepness between P and Q, the 2 points, is going to be the change in altitude over the change in the horizontal. So basically, it's like the rise over the run. But the change in altitude is going to be the change in height from P tilde to Q tilde. So this is just another set of points, P and Q. But it's the same points, just in a 3D sense. So that one gives us a sense of the change in altitude. And then the contour map should give us a sense of the change in the horizontal. So the horizontal, the distance from P to Q. Okay. We will discuss the idea that rates of change depend on direction when it comes to directional derivatives in 15.5. In single variable calculus, we measure the rate of change by the derivative f prime of a. In the multivariable case, there is no single rate of change because the change in f of xy depends on the direction. The rate is 0 along a level curve because f of xy is a constant along a level curve. And the rate is non-zero in directions pointing from one level curve to the next. Okay. So let's continue. Now let's see something. Okay. Yeah, when we say the change from P to Q, that's on the contour map. And so what's that horizontal distance? That'll give us the horizontal distance from P to Q. And then the distance from the change in altitude from P tilde to Q tilde will give us our rise. So it is still rise over run. Okay. So let's look at this example 8. So let's let's see. So example 8. So this example asks us to find the average. So let's copy and paste so that we have about another minute that we can do. So let me see one other thing. Well, let's see. So let's just copy. Oops. I just want to add a page here. And paste. I feel like we're about to get interrupted again. All right. So it says compute the average rate of change from A to the points B and C to B, C, and D in figure 16b. So we need figure 16b. There's 17, there's 16, it says 16b is here. So let's take a picture of this.